Okay, it started. Great. Screen is visible, I'm audible and visible, so we can start. Okay, so slide 4, and today we will be mainly going through biological treatment again because it's a way bigger part of the wastewater treatment plant. And then we will have a small at treatment that is going on in salar wastewater treatment plant. However, there is also a lot of interesting part about nitrogen and phosphorus removal. However, there's a lot to cover, and there is a lot to cover overall. So that's why we will not stop on nitrogen and phosphorus removal, but instead I'll be sharing with you some lectures with way better explanations so that if you are interested, you can go and later look at it. And I would highly recommend you do so. Why? Because actually, in Uzbekistan, in Tashkent, there isn't any wastewater treatment plant that specializes in nitrogen and phosphorus removal, although they should. So maybe having a better knowledge about this part would help us later to decide whether our Tashkent or whether should have nitrogen and phosphorus removal or whether they should, right? So I attend lectures, and you're advised to watch them. It's not your advice. So, okay. So what do we do today? Today we're covering more about return sludge during wet seasons. As I promised yesterday, we will look what will happen in a rainy season. And today we will be also talking about sludge wasting. Today we will be talking about dimensioning on sector clarifier. We will be talking about the concept as balloon sludge. And as I said, we will have some introduction to chemical treatment with sodium hypochlorite. Okay. So we will start off with cultivation. So as I said, make sure that you have everything ready. So to have a quick recap of what we had yesterday. So we have biological treatment, and after biological treatment, we have a clarifier that will separate clean water from this sludge. And we had exactly the same problem. We wanted to calculate XR. XR meaning the concentration of sludge in the return flow, right? So we wanted to calculate it. And the only difference from this problem, from yesterday's problem, is this value. So yesterday our flow was only 500 meters cubed per hour, but today it's raining our wastewater treatment plant, so it doubles. It becomes 1,000 meters cubed per hour. So your task right now is to calculate XR based on these numbers. Yes. So just to mention, if you forgot some of the things, it is 4 grams per liter. XR, so XR is this return flow rate, which is 400. The simple X will be 1,000, right? So the rest is here. So you should just calculate XR. I guess like 2 minutes should be enough for you. Make sure that your units are correct.
Sorry, what was QR again? Like the Q. Okay, clear.
QR was 400.
Mm-hmm.
Okay. In fact, if you are still converting, I just noticed that in fact there is no need to convert this unit. Sorry, there is no need. So you can just directly calculate it. Because at the end you want to get something with grams per liter, so no need to convert them. Yes, it's 14. What was X? Which X? XR or XAT? XAT is here. XAT is 4. XAT is the concentration of sludge, meaning bacteria, inside of the biological treatment unit, aeration tank.
So XR is concentration of bacteria in sludge.
In return sludge.
Okay, in return
here.
sludge.
This yellow stuff, and you need to find this XR.
Yes, I also got 14.
Great.
Here.
So basically, what are we doing? We're summing Q plus QR which is 1000 plus 400, we will get 1400, and we will divide it by QR again. So, and multiply it by XAT. So which will be 1400 times 4 divided by 400, and at the end we will get 14. So now it means that the concentration of bacteria in the return flow is 14 grams per liter. However, we should check whether it is feasible, whether it is a real number. So if you remember last lecture, I showed you something about this sludge volume index, meaning the maximum packaging of bacteria, right? The maximum, the minimum volume that the bacteria can get, which was SVI. So sludge volume index. And using this SVI, in fact, we could calculate XR maximum, meaning the maximum concentration of bacteria inside of the sludge, right? So how we would do so? We would take 1,200 and divide it by SVI. And usually SVI ranges from everywhere between 100 to 150. To 150 milligrams per liter. So now I do the calculation. If you take, so it's not really visible for you, but if you take, for example, SVI to be 100 milligrams per liter, which is usually representative of good bacteria, of bacteria that can settle in a good way, what you will get is you will get 1,200 divided by 100, which will be 12. So meaning that the maximum, maximum concentration of bacteria can be only 12 grams per liter. However, what we are getting is 14 grams per liter, which means way higher. We cannot have this number. So what will happen? It means that in a small volume, we have more bacteria. And as a result, in a rainy season, this yellow stuff will not be this low, but this yellow stuff will increase and will go to the edges of the secondary clarifier. And in the rainy season, what will happen as a result is that this water that is going in the upper layer will just wash out our sludge. And at the end, we will not get clear water that you saw yesterday in the video, but we will get a browny water with sludge and bacteria inside, which we don't want, because bacteria is also BOD, right? But we want to get rid of BOD. So that's why in a rainy season, we should be very, very careful. So what can be done in order to mitigate, in order to address this problem? First, this XAT here. So we can base all this on our formula. For XR to be low, which we want to be lower than 12, our XAT should be lower, right? So because they are like prima proporzionale. So XAT should be lower. XAT minimum can be 2 grams per liter. So you can lower once XAT, which means you can lower the concentration of bacteria that you have in aeration tank, or you can increase the QR, meaning the flow rate that is refluxing your wastewater, right? Either increase this one or decrease this one. Increasing this one is easier. So in rainy season, what usually technical, so there is like a technical person in the wastewater treatment plant that always operates. They're called operators. In rainy season, they usually just increase this flow, and that's it. And in that way, they somehow try to tackle this issue. Yeah, but usually if design was good enough, then you should just put more of these clarifiers and then you will not have this problem. But if you do, then you just increase this one, because decreasing the concentration very fast, it's a bit not feasible, right? So yes, so this is what happens during wet seasons, and you know that now. So good. Okay, now this one we covered. And one thing that you should also know is sludge wasting. So sludge wasting, so as I said in the last lecture, the concentration of bacteria inside of your biological clarifier should be about 4 grams per liter, no higher, no lower, ideally. And what happens with bacteria? As time goes on, bacteria start to grow, its population grows, and its concentration will grow. And that's why you will have to always waste some of those bacteria. So you will, at some point you will not return the bacteria back to home, but you will go and throw away some of the bacteria in order to keep the concentration constant. And basically, everything that defines that is QS and XR. Oh, sorry for these terms, but we have to live with this. So this is QS and XR, basically, and they are determined by these things. So basically, XAT and VAT are the components of the biological aeration tank, and the only thing that you might not be familiar is Y. Y is rate of bacteria growth, and BX, we covered last lecture, this is sludge loading rate. And if you know all of these numbers, you can calculate QS. And if you know QS, then you can calculate solids retention time, meaning for how many days your bacteria is going to stay inside of your aeration tank. Later, you might or may not need this. So it's better that you know this than you don't. And usually, as a rule of thumb, we usually waste about 2% of whatever is coming in, right? So this way is easier. Okay, so no problems here. Now we go with secondary clarifiers. So secondary clarifiers are these things. And in magnified version, they end up being like this. So as you see, this is a round-shaped object, and at the bottom we have sludge. At the top we have water, ideally separated, right? So in order to be able to design secondary clarifier, the only thing you need for now, is just to be able to find their volume. So I guess Ahmad Khan, Gulyara, and Sevinch have already done some tasks on finding volume of primary settlers, right? Primary sedimentation tanks. And it's something slightly similar, maybe a lot similar to this. So usually, in order to find the volume, the only thing that you need is diameter, meaning from which you can find the radius, and the height of the tank. So if you know the radius and the height of the tank, then you can find the volume of the whole thing, right? And the height is already usually given to you. It's prescribed. It should be somewhere around from 1.5 to 2.5 meters. So you choose in between, usually 2 meters, right? And the radius you can find from the area of the secondary clarifier. And now we go into more formulas, so be ready. So there is one thing which is called surface loading rate, meaning how much water we send to the fixed amount of area, right? How much flow goes to the fixed amount of area, which is called surface loading rate, and it's a fixed number, and it has its own it has its own optimum range. So it's usually defined by the flow of wastewater that's going to secondary clarifier divided by the area. And then you have your sludge concentration X and SVI that we have already covered. And then there is another thing, new thing, which is sludge volume loading rate, meaning how much sludge you are allowed to send to the secondary clarifier, right? Not like you're allowed, but you're recommended. And it again has its own formula, which is SVLR, which is given by this one. And this SVLR usually has its own optimum range too, which is everywhere from 0.3 to 0.4. And now, what is our algorithm? So our main goal is to find volume, right? So for volume, first we need our radius or diameter. Diameter we can find from area. Area we can find from V0, and V0 we can find from SVLR, right? So now that I assume that you understood it, we will solve this problem. So you will need to find the diameter of this clarifier, and you're given SVLR, which is 0.3, and you're given SVI, which is 100. You have the flow rate, you have the X, and will you need QR? I guess you might not. Yes, you will need QR. Yes. So yeah. So here is QR. So they are saying that the reflux, meaning how much you recycle your flow, is 0.5, meaning you recycle 50% of what is coming here, right? So now we need to solve this. And I'm thinking maybe I solve it for you so that it would be a little bit more understandable. What do you think? Should I solve it for you, or do you want to try it yourself?
It doesn't matter. But what's the value of X here?
The value of X is 4 grams per liter. So I will give you a first hint then. I think I'll just give you a first hint. Here.
V0 is equal to 0.75.
Yes. So the first thing here that we should do is to find V0. In order to find V0, we have everything. We have SVLR, we have SVI, 1000 is given, X is given. So we should just find V0 first.
Is the diameter 92?